Hello, everyone. How are you? My name is Juhyung Kim. The research topic I'm presenting today is a multi-channel hair-through filter using active noise control formulations. The experiment was done with Yongjae and my advisor is Professor Liu. We are all from Hair Laboratory at Purdue University. I'll start talking with introducing the concept of multi-channel hair-through filter and its applications. Then I'll introduce how the traditional method would work, which is in this case direct inverse filtering, and compare this with the proposed method. I will also cover the control system, including how I set up the experiment, and move on to the results and conclusions. We know that the sound signal is altered when there is a blocking material. Due to these distortions, people would hear distorted sound. To solve this problem and help people listen more natural sound and have natural communication experience, properly designed hear-through filter can be used. Especially in this presentation, this will cover a multi-channel case which will reproduce the desired signal in three-dimensional open spaces. In the single-channel case, the application would be limited mostly about earphones or headphone cases. And also, here, the stability constraint is also considered to make the filter realizable. Having it multi-channel would provide more room for more complicated development in providing realistic interacting experiences in separated spaces. It has been pretty common things to have blocking materials while communicating for the virus spreading prevention during COVID-19 era. If you go to banks, classrooms, you probably have experience of seeing an awkward panel and communicating through those was a little bit hard. Also, this can be used in hear-through setup for vehicle or conversation in hygienic environments such as hospital or classrooms or office setup. And this can be expanded even in augmented reality or virtual reality. To make it feasible, what we have here today is one-way setup, but we're planning on to produce two-way multi-channel hear-through systems. For the effort to construct the desired sound field, there is a traditional method, direct inverse filtering. An inverse filtering technique is to eliminate the unwanted signal and reproduce the desired sound field by using matrix inversion. However, it cannot react to the sound liquids because it is calculated by taking the direct inverse of the frequency response matrix of the prominent path. And a delay would be needed to make this causal. And this delay would cause a comb filtering effect, which causes to distort the sound. And also we need to have equal number of reference microphones, control speakers, and error microphones. Those constraints would limit our experiment in these cases. The proposed method will provide a solution to alleviate the comb filtering effect by reducing the distorted sound liquids coming around the blocking material using active noise control structure. It does not have limit on having different numbers of microphones or speakers to it. For both method, basically, The goal is to reduce the difference between the sound with the barrier and without the barrier. Without the barrier, the sound passes through the path we call M, and that will produce natural communication environment because there's nothing to distort the sound. However, when we place a barrier in the propagation path, this will distort and delay and possibly even attenuate the sound signal. The direct inverse filter approach was realized in this paper in such a way. We let M, the frequency response when we don't have the barrier, equal to what we have in the setup. So we let M equals B plus GW, and by doing a little bit of work here, we can acquire W inverse. And this is done by taking inverse of GE. Therefore, we need to add delay to make the filter coefficient causal. As I said, because of this delay, it is very hard for us to match with the delay of the signal coming around the panel, which will eventually produce the comb filtering effect. Let me briefly explain what the comb filtering effect is. This is one of the problems usually faced in this case. So sound reflected by the obstruction in the propagation path and delay from the filter design can cause time delay difference. This will produce a distortion in the sound signal, a comb filtering effect. This is called comb filtering effect due to its shape in the frequency domain plot, as you can see at the plot. In the plot, the red line behind represent the original signals, and the blue dots is the delayed signal. And summing those two will be the yellow line. You can observe that the shape of the yellow plot follows its name. As you can see, the problem here is we have distorted sound. To help people communicate better and as natural as possible, we could use our proposed method to minimize the error function. Again, at the top of the page, we have the M, the frequency response in the situation when we don't have any obstructing material in the path. And then below is the control setup. So combining those two, we could easily set up an error function. Primary goal here is to minimize E tilde, which is Y minus Y prime, to reproduce the desired setup. The combination of these two will be this setup. So this is the detailed control system, and we have control filter W, and its output passes through GE, and it meets attenuate signal due to panel. Arrow signal we're looking for is not the Y here, just like normal ANC structure, but it is E tilde after this. Here we assume a perfect model in nominal operating conditions, meaning G hat equals to G. This will result in a simple standard feed-forward system as this. Delta here is specified delay between desired sound and reference signal. And by using the ANC structure, minimizing error function can be achieved. But here, even if the estimate of the acoustic feedback path G hat is assumed to be perfect in nominal operating conditions, the stability issue caused by the closed loop WG in the controller H should still be considered. Because for the entire system to be stable, here H should also be stable. And also in this case, we take a three-dimensional open space into consideration. It creates relatively susceptible environment to its acoustic feedback path, as you can see in the picture. This is the animation representing the acoustic feedback path of the experiment setup. So we have a signal coming from the control speaker going in to the reference microphone, and this will create acoustic feedback path. To have the stable filter coefficients, we imposed Nyquist criterion for the stability. And let's move on to the experiment setup. And this is the experiment setup we have. We've used sampling frequency of 4 kHz, and we have filter length of 128. We have anti-aliasing and reconstruction filter, and those cutoffs are at 1.5 kilohertz. And these are the distances, and units are centimeters. At the leftmost side, we place speakers, and after the speakers, we place reference microphones. And in between the reference microphone and error microphones, we place a panel, which will deliver the distorted sound signal to the error microphone. And after the panel, we place 2 control speakers, and this will help alleviate the calm filtering effect. And here is the result of having stability constraint. On the left-hand side, the plot is the value of the rear part of the maximum eigenvalue of WG. And for the convenience, I plotted for the negative values of these so that we could observe in the positive y-axis. So when the stability constraint is not considered, we could observe that the graph go over 1 in some frequency bands and make the system unstable. But in the case where the stability constraint isn't considered, it shows a good stability around all frequency band up until 2000 Hz, which is the half of the frequency sampling frequency. And let's take a look at the result. This is the result we got from the experiment. We have the green line, which represents the desired signal. And we have the red line. This is the result that we got by using proposed hear-through filter. As you can see, the red line successfully follows the desired signal, and the inverse filter response is simulated and is not stable, which is hard to be realized in the experiment setup. And the result we got from the inverse filtering is in blue color. Comparing this with others, there's much difference due to the calm filtering effect. You might not notice that this is the calm filtering effect, but I gave more delay to have more peaks in the frequency plot as this. So basically, the delay given here can be adjusted depending on how long the acausal part of the impulse response of the filter is. And obviously, when there is a complete isolation of the sound in the experiment or in the real situation, direct inverse filtering technique might work well. However, that wouldn't be a very realistic case. From this plot, we can observe that the hear-through filter can achieve a lot better result with alleviated calm filtering effect. In conclusion, the proposed method showed a good result in the multi-channel hear-through applications. And this proposed method has potential to be expanded for more complicated applications as it provides a global control of the sound. And we can use it in vehicle hear-through, augmented reality, or virtual reality. And these are the references that I use for the paper and the presentations. And these are the contact information of the authors of the papers. And this is it for the presentation I have. Thank you very much.